Ladies, thanks for joining me. We're going to look at inverse functions. So let's first talk about inverse notation. The inverse of f of x is notated by f raised to the negative 1 power of x. Now you do not read that f to the negative 1 power, but you read that as f inverse of x. So this negative 1 power notates inverse. So this function f of x is equal to x plus 3. And if we plug in an x value of 1, we have a y value of 1 plus 3 is 4. If we plug in 2, 2 plus 3 is 5. Plug in 3, 3 plus 3 is 6. Plug in 4, 4 plus 3 is 7. So I've given you the function x plus 3 and shown you the input and the output. Well, let's talk about what is the inverse of x plus 3. The inverse of x plus 3 is x minus 3. So our inverse function, f inverse of x, is equal to x minus 3. And I'll show you in a few minutes how to actually find the inverse function and how to verify. But if you think about what is the inverse operation of adding 3, you would hopefully say subtract 3. Let's see what happens, what ordered pairs we get with this inverse function. I would like to let x equal 4. When we plug in 4, 4 minus 3 is 1. Good. Let's try plugging in an x coordinate of 5. 5 minus 3 is 2. Let's plug in an x coordinate of 6. 6 minus 3 is 3. And let's finish up with 7. 7 minus 3 is 4. Now I would like you to notice what happened to our ordered pair 1, 4. If you look at 1, 4 in the original function, you have 4, 1 in the inverse function. And we have an ordered pair of 2, 5 in the original, 5, 2 in the inverse, 3, 6 in the original, 6, 3 in the inverse, 4, 7 in the original, 7, 4 in the inverse. So what can we say about that? We can say that f and f inverse have the effect of undoing each other. How do you undo plus 3? Well, you subtract 3. We can also say that the domain of f, so here's the domain. Here's the domain of f, 1, 2, 3, and 4 equals something about the inverse. So compare the domain of f to the inverse function. What do you notice? Did you notice that the domain of f is equal to the range of f inverse? And then let's look at the range of f. 4, 5, 6, 7. The range of f is equal to something that has to do with f inverse. Did you notice that the range of f is equal to the domain of f inverse? So inverse functions, the actual equations should undo each other. If we undo 3, we undo that by subtracting 3. To undo subtraction of 3, we add 3. And then we can also say that the domain becomes the range becomes the domain. So the ordered pairs switch. So our first goal after that brief discussion is to find the inverse functions and verify that the two functions are inverses of each other. Example A, we want to find the inverse of f of x equals 5x. To find the inverse function, we first rewrite this as y equals 5x, just to make things easier when we are about to solve. So we replace f of x with y, and now we swap x and y out. And why are we allowed to swap those? Well, we've just shown that the domain of f becomes the range of y. The range of f becomes the domain of y. So we can swap x and y out. So we replace f of x with y, then swap x and y out, and finally we solve that equation for y. And to solve this for y, we have y is equal to, we would have to divide both sides by 5. Y is equal to x divided by 5. So we can say that if f of x is equal to 5x, then f inverse of x is equal to x divided by 5. So once we find the inverse, how do we verify that f and f inverse are inverses of each other? To verify that, we will find f of f inverse of x. What does that mean? It means, remember, f inverse of x becomes our input. So we'll find f of x divided by 5. So if x divided by 5 is our input, then we will replace x in f of x with our input. When you simplify this, the 5's cancel, and that equals x. When you have the composition of f inverse into f, if that reduces to x, then you have undone, like we said, you have undone the function. Now, not only should we test f of f inverse, we should also test f inverse of f of x. So now, what becomes our input? 5x becomes our input. So we'll plug 5x into the x coordinate of the inverse function. So that gives us 5x divided by 5. What does this reduce to? This also reduces to x. So when the composition of f inverse and the composition of f inverse of f both equal x, that verifies that the two functions are inverses of each other. So I should not say verify that f equals f inverse. I should say verify that f and f inverse are inverses of one another. I know that sounds a bit confusing. How else can we verify? We can sketch the graph of both of these. So I want you to take a moment, and I'd like you to graph y equals 5x and y equals x divided by 5 on the same coordinate plane. Please pause the screencast and complete that now. Okay, so I've graphed y equals 5x, and I've graphed y equals x divided by 5. So how does this verify that these are inverses of each other? Well, let's compare a few of the ordered pairs. We have an ordered pair of 1, 5, and we have an ordered pair of 5, 1. Did the domain become the range and the range become the domain? Yes, and that should happen with all of these points. So when these points switch places, I want you to see where the symmetry lies. The function f and f inverse should be symmetrical to one another across the equation y equals x. And how can we confirm that it's symmetrical across the equation y equals x? These are equidistant from that line. and that shows that. So something you need to gain from this are two things. To verify that two functions are inverses, you should be able to plug the function into the inverse and you should be able to plug the inverse into the function and the function into the inverse. Both should reduce to x. If both reduce to x, you have inverses. If they do not both reduce to x, there is no inverse between those two functions. Also, you should be able to sketch the graph of each function, and they should be symmetrical across the line y equals x.